So the next lecture in the electric field section of this Unit 3, which is electric, gravitational, and magnetic fields, is about electric field lines. And we're going to look at this. We're basically going to take a part of section 7.3 from the textbook and look at it a bit more in depth. And when we're talking about field lines of any field, basically we're talking about the individual vectors. How do we represent the individual vectors of the field? And those vectors imply a type of force that a test object would experience at those different locations. Now, when we have a gravitational field, the field lines, the gravitational field lines, are always going into the source. When we have an electric field or other polar fields, what happens is we have two states. We have the positive state where, because we always look at a positive test charge. In the positive state, the field lines would be radiating out, and in a negative state, the field lines would be radiating in. And this is based on the idea that we always use a positive test charge. So, quick little question for you. Of those two images you see there, A and B, which one of those matches a gravitational source? And the correct answer would be the B image, which is the negative charge, because a negative charge has an attractive field lines. Now, this is all based on a positive test charge. If our charge was negative, those field lines would end up repelling. So there is something else to consider as well. The convention is we always consider a positive test charge. So the convention is when we draw a singular charge on its own, if it's positive, we show the field lines radiating out, and if it's negative, we show the field lines radiating inward. So these field lines are parallel to the electric field epsilon, and the density of the field lines is proportional to the magnitude of epsilon. So in both parts of the diagram, the field lines are densest near the charges, and in both cases, the magnitude of epsilon increases as the distance to the charge decreases. So the closer we are to the charge, the greater the vector we draw should be, because the stronger epsilon is, and the greater magnitude of the charge, the stronger epsilon will be as well. This is based on the inverse square proportionality of the electric force equation, and it's also based on the product of the charges of that equation as well. So I'd like you to copy this down. You may want to pause to do that. Electric field lines are continuous lines of force that show the direction of electric force at all points in an electric field around a charge. And I'd like you to draw those two, and you could also copy that recall down as well, which basically tells you the same thing I said previously, that the electric field lines of a gravitational source represent are the same as what we would see for a negative charge. So here's a thought question. How do two-point charges that interact through Coulomb's law know about each other? So how does one charge transmit electric force to the other? So if we're considering the electric field lines, every charge generates an electric field, and that electric field generates an electric force, or rather it transmits an electric force. So if these two charges, they don't interact directly. If two charges are near each other, it's the interaction between their electric field lines that causes a force. And that force could push these charges away from each other or attract them towards each other. Now with electric charges, one thing we also consider is when we have two singular charges or sets of charges that are near each other. And this is what when we have this, we basically would have two charges that are on a one-dimensional plane. And we call this an electric dipole. The distance between them is given r. And the dipole, we have a couple arrangements. We have but essentially the two that we end up having are the opposite charge dipole and the alike charge dipole. So let's show you what these dipoles would kind of look like. Let's consider the opposite charge dipole. Now on this slide you have your field lines from a negative Q alone, so a negative charge. All the field lines are radiating inward, and the positive charge, all the field lines are radiating outward. And we know that opposite charges attract. So if we ended up having these two charges in a dipole that were near each other and the r was relatively close, what would happen, or rather relatively small, the r would be relatively small. What would happen is the lines would kind of bend in the way that's shown in that second image. So we have generally the field lines are going from Q to negative Q, so positive Q to negative Q. And that, for example, the field line that would be going directly up or directly down from positive Q would now start to interact with the field lines from negative Q. And when we add those field lines together, a vector addition of those, the direction starts to change. So this is what our electric dipole would look like when we have a positive negative charge. Now the two like charges arrangement would be shown like this. So we have for Q positive charges, the lines usually radiate out. In this case, what would happen is the lines would be radiating out. However, our negative charges would be the same. If it was two negative charges, it would look the same, except that the arrows would be pointing the opposite way. So you can see at the point directly in the middle of these two charges in this electric dipole, the electric field at that point is 0. And that's because the field lines from, assuming that these Q's are both the same magnitude, the field lines would add up together in a vector addition, and one would be going to the left, one would be going to the right, and they would add up to 0. So this is our arrangement of an electric dipole of two like charges. Now that's not the only type of dipole we can have. If we increase the magnitude of one of those dipoles, we start to have other different arrangements. You won't really need to know many of these past 2Q and Q. And this one here is a plus 2Q and a minus Q. So for plus 2Q, that's a stronger electric field. So it's twice, every time we kind of take find out the magnitude of this electric field at a point away from, at a point r distance away from 2Q, it will be twice as large as the magnitude at the same distance r away from negative Q. Now the dipole ends up having this kind of, I always think of it as a butterfly wing arrangement. We have an overshoot past 90 degrees past the negative Q, and it kind of hooks back around. So it kind of looks like a butterfly wing. So I call this the butterfly arrangement. I don't know if many others do. But this is our electric dipole. We have twice the charge in one charge, and if they are, one is positive, one is negative. So, considering all of that, we've looked at dipoles. What if we take an entire plane and we add we charge one entire plane or plate as positive and another plate as negative? What happens here is we could end up creating a uniform electric field between those. So it's going to be shown on the next slide, but I'll kind of explain it here first. One of the issues with our dipole is that at any point the magnitude of the electric field is different. It's not uniform. It kind of changes as we move through the electric field generated by the dipole. But if we have a series of charges on a plate, and this can be done by basically charging a conducting plate with the same charge throughout, and we put that near another plate, we can end up creating a uniform electric field between those two plates. Uniform meaning that at any point located between those two plates, the epsilon will be the same magnitude and the same direction, which makes it very useful for some engineering applications or other applications that we can come up with. And the plate's really only useful when we have opposite charges, so that it's going from the from positive to the negative. So let's look at what this field looks like, and this image shows it here. Basically, the lines go directly from positive to negative. The plate or the field between the plate is uniform at all locations. It's perpendicular to the plates. The only problem is that near the edges of the plates we start to have this kind of hooking, where basically the electric field is kind of jumping from the edge of the plate to the other edge of the plate. But between in the main area between those two plates, our electric field is uniform. It is straight, and it was perpendicular to the plates, and each field line is parallel to every other field line. And this creates a uniform electric field. So outside of these plates, the vector sum of the electric field is 0. But within the plate, we have an epsilon that we can then use to for a number of different applications, and we'll be learning many of these throughout the course. But let's look at how we can work with that on this next slide. So it says here, as long as the separation between the plates is much smaller than their surface area, the electric field between the plates is uniform. In fact, except near the edges, the magnitude of the electric field depends only on the amount of charge. So I mentioned that a bit earlier. At the edges, we start to have that hooking effect. I'd like you to copy this down. And again, you may want to pause to do that. But this explains parallel plates of charge. I've already kind of repeated this, except for the second bullet point, where it says, except near the edges, the magnitude of epsilon depends only on. So this is how we can increase that epsilon. We can increase the charge on the plates, and that charge Q is an equal charge usually between the positive and the negative. We can change the area, and epsilon is inversely proportional to the area. So if we want to increase epsilon, we decrease the area. We can also change the material. So different types of conducting material would be able to make epsilon larger or smaller depending on what we need to. So here's a question. It says the electric field intensity at point M between two oppositely charged parallel plates is epsilon. What effect will each of the following changes considered separately have on epsilon. So if the distance between the plates is halved, what would happen? And there would be no change. The distance between the plates doesn't have an effect. If you looked at the previous slide, and we'll just go back quickly, the distance between the plates is independent to the epsilon. Next question. If the amount of charge on each plate is tripled, so if we triple the Q on these plates, we would triple the epsilon. The electric field would triple in strength. If we halve the plates, it's inversely proportional. So if we halve the plates, it's essentially the same as dividing by 0.5. And dividing by 0.5 is the same as multiplying by 2. So we double the strength of the electric field. So I'd like you to try the questions out for this part of the lesson. And what you can do when you're done this is go back and kind of review the previous questions in section 7.2, 7.3, because now that you understand the electric field lines a bit, it might make it a bit easier to understand how the electric force is transmitted.